right, well, let's go ahead and progress into chapter 11 now, and we're going to begin studying shapes. I mentioned to you that analytic geometry was pretty much shapes like we studied in geometry, but we're going to put them on the Cartesian plane and study them, and study all kinds of different aspects and observations about them. We're going to blend, marry, if you will, algebra and geometry together. So I want to begin by reviewing an algebra concept, and then we're going to apply some geometry to it a little bit. But as we study shapes, I want to start with the most basic shape of all. You go back in your mind to geometry, the most basic shape of all would be a straight line. A point doesn't actually have any shape, but a line is composed of an infinite number of points, even a line segment, which is more specifically what we'll study. So we're going to begin our discussion in chapter 11 by talking about linear equations. Linear equations. Equations that are graphed as straight lines, equations that have x to the first power and y to the first power. No squares, no cubes, no nothing weird, just nice, easy equations like we talked about all the way back in Algebra 1 and Algebra 2. But as I mentioned, we want to take some geometry concepts to these. So as we talk about straight lines, in geometry we said if we want to measure a line segment, or for instance if we want to say that two line segments are equal, what is it that made in geometry two line segments equal to each other? Well, we didn't define it quite that way of saying length. How do we define equal segments in geometry? Line segments whose endpoints can be made to coincide, right? And in fact, when we measured line segments in geometry class, we didn't use a ruler, because that's not a geometric instrument, remember? What did we use to measure line segments in geometry? A compass. Because all we cared about was the distance between the endpoints. That's how we determined the length of a line. How far apart are the endpoints? And if the distance between these endpoints was the same as the distance between these endpoints, the line segments were equal. So as we talk about linear equations, one of the first things we want to talk about is this concept of length of a segment. And it is, of course, then defined as distance between the endpoints. The distance, it's a horrible W, distance between endpoints. It wouldn't be so bad if there were people in here who knew how to write cursive. All right, distance between the endpoints. Quite keeping me honest here. All right, so the length of a segment, distance between the endpoints. Now, I want you to imagine for just a moment, and for sake of time, we'll just do a quick sketch Cartesian plane here. Let's suppose we had the point 2, 5, and we had the point 2, 2. And I wanted to measure the length of this segment. That'd be really easy to do, especially if it were on graph paper, because you'd literally just count up 1, 2, 3, right? 3 units long. If I wanted to measure the distance between 2, 2 and 6, 2, that'd be really easy to do, wouldn't it? I could just count for that matter. 1, 2, 3, 4. Right? 4 units. We can count that. But if I wanted to find the distance between 2, 5 and 6, 2, well, you know as well as I do, they don't have tick marks going this direction, right? All the lines on the graph paper go vertically and horizontally. How would I calculate the length of this segment?
Pythagorean theorem.
Pythagorean theorem, right? Vertical lines, perfectly vertical lines, easy enough to figure out the length. Perfectly horizontal lines, easy enough to find the length. But you know as well as I do, how often does a line actually run perfectly horizontal or perfectly vertical? Rarely. So if we want to do this, we'd have to use the Pythagorean theorem. Well, essentially, in the Pythagorean theorem, you'd be calculating the distance between these x values, or the change in x squared. You'd also take this change in y's squared, then you take the square root. That gives us then our distance formula. Write this in your notes. D equals the change in x squared plus the change in y squared, and of course the square root of all of that. So since we already knew that the change in x was 4 units, since we already knew the change in y was 3 units, what would be the length of this segment between 2, 5 and 6, 2?
Square root of 21.
Ooh, careful. Square the 3.
9.
Square the 4. 16 and 9 gives?
Or
It was
positive
25, and we take the square root of 25. Now, Quentin's answer was positive negative 5. Can we have negative lengths? Not really. So we'll just say 5 units. So here, 5 units long is the length of that particular line. Does that make sense? All right, look in your textbooks, if you would, at page 203. By the way, do you remember the distance formula from your Algebra 1 and Algebra 2 days? Maybe vaguely, all right? And in Algebra 1 and Algebra 2, we actually have the way the book had it. If you're looking on page 202, you see that distance formula. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. That's the way I taught it in Algebra 1 and Algebra 2. But the lazy mathematician, I'm like, let me show y'all how I do it, because I'm lazier than that. You know the order in which you subtract matters, because subtraction's not commutative. But if you square the result, it becomes commutative because it doesn't matter whether you get a positive or negative, right? So because the order doesn't matter, just say, let's find the change in x, whatever that is, squared, change in y, whatever that is, squared. It's just an easier way to think of the formula, and it's less writing. I am that lazy. Page 203, number 1, they give us these 2 points. They give us the point 2, 3, and they give us the point 3, 6. Looking at the x values, I actually picture this on a number line. How far apart are those 2 points? 2 and 3. 1. Square it? 1. How far apart are 3 and 6 on the number line? 3. Square it? 9. What's the length of the line segment joining those points? Square root of 10 units. If you wanted to get a decimal, what, 3.1, something like that? Right? A little bit bigger than 9, square root of 9, which is 3, so 3.1 would be my guess, but the square root of 10 units. Look at letter B. We've got the point 55, and we've got the point 21. What is the change in the x values? Or positive 3, either way, right? Square it. 9. What's the change in the y values? 4. Square it. 16. What do we get when we take the square root? Well, again, not positive, negative, so we'll just say 5 units, because it's the square root of 25. Again, picture on a number line. Again, forget the positive, negative even. How far apart are 2 and 5? They're 3 units apart. How far apart are 5 and 1? They're 4 units apart. Look at letter C. Here's where you're going to get value in thinking of how far apart are the points. Picture the number line. How far apart are 4 and negative 3? 7 units. 3 to the 0, 4 beyond the 0, right? 7 units squared? 49. How far apart are 2 and negative 3? 5 squared? 25. Add them together, we're going to end up with the square root of 74 units. Do you see how instead of doing x2 minus x1 squared, or what, just faster and easier to think, how far apart are they on the number line? Letter D, looking in your textbook, what's the change in the x? 2. From negative 5 to negative 7, they're 2 units apart. Squared is? 4. Look at the y values, how far apart? 14 units apart. Squared? 196. That's one we should have memorized in our earlier years, but may have forgotten 196. Good refresher. So we have 4 and 196. Add that together, you get 200. So we have the square root of 200, but we're not going to leave it that way. Because I could factor 200 into, I could do better than that. How about 100 times 2? Right? Where we take the square root of 100, 10 times the square root of 2 units. So a reminder that we'll rationalize or reduce all irrational radicals. Questions on the distance formula. All right, I want you to do number 2, find the distance between the points A through D. Do all 4 parts of number 2. Finished with all four? All right, letter A, excuse me, of number 2. What did you get for the length of the segment, Jamie?
5 units.
5 units, very good. Change in x3, change in y4, square those, take the square root, we get 5 units. Letter B, Quentin.
Square root of 105.
What was your change in x?
6.
Squared.
36.
All right, change in y?
8.
Squared.
That was 64.
64, there we go, that was the problem. And then so 64 and 36 adds together to get?
100. So 10.
10 units, there we go, 10 units, our answer. Letter C. What did you get for the distance, Jamie?
3 times square root of 5 units.
What's the change in x?
3.
Squared?
9.
Change in y?
0.
0 squared is
0.
0. So 9 and 0 gets 9. We're just taking the square root of 9, we get
3.
3 units. 3 units. Should have been our answer. Letter D. Back to Quentin. What'd you get?
5 times square root of 2.
Good. Initially the square root of 50. We're going to reduce that down and say 5 times the square root of 2 units. Is that what you had? Good. Questions on A through D. All right. Next geometry concept we want to talk about as we look at our linear equations is the point that divides a line into 2 equal segments. The point that divides a line into 2 equal segments. Of course, we call that class the divides a line
Midpoint.
into 2 equal segments. Midpoint, right? It's in the middle of the line. So the next thing for you to know about linear equations is how to find the midpoint of a line segment. The midpoint of a line segment. Now, of course, in geometry, we would use compass and straight edge to bisect, right? Perpendicular bisect. You remember that? Compass at one end, open it up more than half, arc above and below. You remember all that fun stuff? Yeah. Well, in algebra, it's easier because we're finding the midpoint. That's the point in the middle. So, of course, we know that a line segment is comprised of an infinite number of points, correct? Or comprises an infinite number of points. It's composed of. Anyway, don't tell Mrs. Henderson. All right, so there's an infinite number of points. But if we were to average all of the x values of all these infinite points, and we were to average the y values of all these infinite points, the average x and y values would be the average point, which would be, mathematically, the midpoint. But there's a much easier way. We don't have to actually average all of them. I could just average the 2 endpoints together. Does that make sense? It would have the same mathematical effect. So to find the midpoint of a line segment, or the average point, what we're simply going to do is average the endpoints. Well, to average something, remember, that means we have to add and divide by 2. So if I add the endpoints abscissas, x1 and x2, and divide by 2, and then add the ordinates of my endpoints and divide by 2, I'll have the midpoint. So for instance, you're on number 2, look at letter A. They give us endpoints of 1, 2, and 4, 6. Well, we want the average, or the middle point, correct? So what would be exactly halfway between 1 and 4? Well, add and divide by 2.
2.5.
5 halves, or 2.5. Right? What would be exactly halfway between 2 and 6? 4. 2 plus 6 is 8, divided by 2 is 4. That's your midpoint. Pretty easy? All right, look at letter B. What do you get if you add the x's together?
2.
Negative 2. Divide that by 2. Negative 1. All right, what about the y's? If you add the y's together, what do you get? Negative 2. Divide that by 2. So what's the midpoint? Negative 1, negative 1. Make sense? Do C and D. Finding the midpoint, obviously, not doing what directions say. You finished? Okay, yeah. You had a look on your face. I'm like, I can't tell if she's done or if she's puzzled. Oh, you're finished. All right. Letter C. What did you get for your midpoint, Quentin?
1/2, 6.
1/2, 6, or 0.5, 6. How about letter D? What did you get for your midpoint, Jamie?
I got, wait a minute, what did I say this? Okay, I got, 1.5 and, 3.5?
Close.
-3.
-3.5. So 1.5, -3.5, or 1.5, -3.5, or 3/2, -7/2 would work, right? Now, if you were graphing that, that would be a little annoying, but it's, we're not graphing them because we're lazy. All right, questions? All right, speaking of geometry then, let's think back to some other geometry ideas. Let's put lots of line segments together, or multiple line segments together to make shapes. Like, for instance, take an example 1. It says, show that those 4 points are the vertices of a parallelogram. Okay, so this is going to take you back to your geometry days. Think back to parallelogram. What do we know about the sides of a parallelogram?
The top 2.
They're parallel. Good. Anything else besides the fact the top 2 are parallel and sides are parallel?
Top 2 are equal and sides are equal.
Opposite sides are equal. Good. Anything else we remember about a parallelogram?
Opposite angles are equal.
Opposite angles are equal. What else? What about consecutive angles?
Add to 180.
Add up to 180. So supplementary was the word we used. What about the diagonals? They're not equal. They bisected each other. Diagonals bisected each other. Let's see. What else do we know about parallelogram? I think that's about it. All right. So it says show that those 4 vertices, A, which is 1, 2, B, which is 6, -10, C, which is 9, -6, and D, which is 4, 6, show that these are the vertices of a parallelogram. Well, I don't know anything about parallel yet, right? But I do know about equal. I could find the lengths of these sides, right? If it's A, B, C, D, right? If that's the name of my parallelogram, bringing back flashbacks like from the given parallelogram A, B, C, D, prove, blah, blah, blah. Yeah, good memories, right? Well, my sides then are AB, BC, CD, and DA, right? Those are the 4 sides of the parallelogram. And these 2 would be opposite sides, AB and CD. And then BC and DA would also be opposite sides as well. If I can find the length of AB and the length of CD, and if those 2 lengths or distances are the same, then I've got equal sides. If I can find the lengths of BC and DA, notated D sub BC, distance sub BC, distance sub DA, right? If I can find those lengths, if those are equal, opposite sides equal, boom, parallelogram, right? Now, they graphed it for us, right? So we look at it, like, okay, yeah, I can tell by looking at the graph, it's a parallelogram, if we trusted our eyes. But I broke you of that habit last year, remember? So we don't know anything about a parallelogram. We got to do the math. So we're going to find the length of AB. Well, what's the change in X? 5. Change in Y? 12. Careful. 12. 5 squared? 25. 12 squared? 25 and 144 added together gives you 169. Square root of 169? 13 units. All right, let's find CD's length as well. If it also is 13, we're halfway home. Change in X?
5.
Change in Y?
12.
Well, you know what this is going? 5 squared, 25, 12 squared, 144, added together 169, square root 13 units. These 2 sides are equal. Does that make it a parallelogram? No. Because if the other 2 sides aren't parallel or equal, then, whatever. Okay, so now let's find BC's distance or length. Change in X.
3.
Change in Y.
4.
3 squared?
9.
4 squared?
16.
9 and 16?
25.
Square root of 25?
5.
5 units. All right, let's find AD's or DA's length. Change in X.
3.
Change in Y. Since they have the same change in X, change in Y, when you square them, add them, take the square root, you're going to get the same 5 units. Since opposite sides are equal, it's got to be a parallelogram, right? There's another way we could do it, though. Remember I said the diagonals bisect each other? Well, if diagonals bisect each other, then that means that the point where they intersect each other must be the midpoint of each diagonal. If it's called ABCD, then that means from A to C, these are going to be opposite vertices, right? So AC is a diagonal. BD is a diagonal, opposite vertices, right? Now, they don't have to be the same length. Most parallelograms have a long diagonal, short diagonal. But if they have the same midpoint, that is, if the midpoint of AC is the same as the midpoint of BD, that would also be another way to prove it's a parallelogram. Not prove in the statement's reason sense, but prove mathematically, prove algebraically. Do you see this marriage between algebra and geometry? All right. So let's find the midpoint of AC. Remember, you're not finding change in x or change in y. You're actually adding the x's and adding the y's here. What do you get if you add the x's? Half that? What do you get if you add the y's? Half that? All right, let's find the midpoint of BD. Add, half, add, half. Since they have the same midpoint, that proves it's got to be a parallelogram. That would have been a lot faster than doing all those distances, wouldn't it? Yeah, you know, you lose some, you lose some. Questions on that? Questions on that? All right, turn over to page 204 now. Page 204. And go ahead and read number 3 for me, if you would, Jamie.
Using the distance formula, show that the diagonals of a rectangle ABCD are equal.
All right, diagonals of ABCD. So which line segments are the diagonals if the rectangle's name is ABCD? AC and BD. It says, show that the diagonals are equal. Again, technically, we're not proving anything here. They are telling us that this makes a rectangle. And frankly, if you look at the points in letter A, 0, 0, 5, 0, 5, 3, 0, 3. Like, you already know that's a rectangle, right? Even just mentally graphing it. So you know it's a rectangle. We know the diagonals should be equal. Let's prove that from A to C and from B to D, the diagonals are equal. Let's find the length of AC and the length of BD. Well, for AC, at your seats, find the length. Study hall, make sure we got good posture, head off hand. There. How'd they do? Did any of you need to visit the library? Sneak you on the back end of the 7th graders' time?
I don't think because we did this one.
That was Friday, wasn't it? What do we get on number 3, letter A, for the length of AC? Good, square root of 34. For AC, it's pretty easy because you got 0, 0, and you got 5, 3. Well, obviously the change in x is 5, square root is 25. Change in y is 3, square root is 9. That's where we get the square root of 34 units. BD is not much harder though, right? Because you got 5, 0, and you got 0, 3. Again, the change in x is 5, the change in y is 3. Of course, it's going to come to the same square root of 34 units since the changes themselves are the same. So again, showing, yes, the diagonals are equal. It's just that in geometry, we had to leave it at they're equal. In analytic geometry, we can actually find the lengths of those equal diagonals. Make sense? With the parallelogram previously, oh yeah, opposite sides are equal. But what is the length of those sides? Or what are the lengths of those sides? They're going to bisect each other. Yeah, but what is the point where they intersect and they bisect each other at? What is that midpoint? So we can answer more as we marry algebra and geometry together. Happy Valentine's Day, except that was yesterday. Number 4, read that for us, Quentin.
Show the quadrilateral UVWX is a parallelogram.
There we go, some good big words in there. Well, 2 ways I could show it's a parallelogram. Midpoints of what?
The diagonals.
Show that the midpoints of the diagonals are the same, or
The sides are
show the sides are equal. Show the opposite sides are equal. Let's do it both ways, because why not? If I've got U, by the way, I like to draw sketches. Now, The sketch doesn't have to be oriented accurately. Here I did have it oriented somewhat accurately. Here I'm not going to because, too lazy. And so I've got these points here. But it might make it a little easier when you see a picture to say, okay, what's the distance from U to V? Dove. What's the distance from V to W? What's the distance from X to W? What's the distance from U to X? Ducks. All right, exercises, find those lengths. Find the lengths of the sides of what they're telling us is a parallelogram. We're showing that, yes, it is indeed. All right, did you get those lengths? Square root of 5s for UV and XW, or 3 square root of 2 for the UX and VW. Okay. Now let's find the midpoint of both. The midpoint of VX and the midpoint of UW. And show that either way you saw fit to prove this would work. Or show this, not prove it. If we add, we get divided by 2. Add, divide by 2. 5.5, 5.5. All right, if we did here, add the x's, we of course get 4 divided by 2 is 2. Add the y's, divided by 2 is again 5.5. And again, that shows, yes, this is a parallelogram, as if we hadn't already shown it previously. Questions on that? All right, number 5. Here's a fun one. Jamie?
Show that triangle XYZ is isosceles.
Now you understand that even if it's not in a plane, even if you're in 3 dimensions, 3 points always determines a triangle because you can't bend a triangle. Triangles got to be rigid, okay? So you've got a triangle with 3 points. That means triangle. But to show it's isosceles, what does that mean?
That's part of the parallel.
What does isosceles mean?
2 sides are equal.
2 sides are equal. And so what do I need to do to show that these 3 points give me 2 equal sides? Find the lengths of all 3 sides, and 2 of them should come out equal. If they do, it's isosceles. So I'm going to draw a sketch, and I don't really, notice I'm going to draw it almost looking equilateral, because I don't know which sides are going to be the equal sides. Let's draw a quick sketch, and I say, okay, x is negative 2, 7, and y is 6, 5. And z is 0, negative 1. Let's find the lengths of all 3 sides, and 2 of them should come out the same, at least if indeed this is equilateral, like, or isosceles, like it claims. Set your seats, find all 3 lengths. Bless you. Alright, did you get these lengths? Did you get 2 squared is 17 or square root of 68 units for xy? And then same thing ended up coming in for xz. Same thing. I got that 68, so I knew it was going to reduce. And then here I ended up getting 72 or square root of 72, so 6 square root of 2 units. Any questions at all? So which two sides are the equal sides?
xz and xy.
So which two angles are equal? Could you see that being a question? Given these 3 points, which angles of the triangle are equal? Oh.
Z and y.
Angle Z and angle Y are the equal angles. Now, I don't know how big those angles are. That's coming, by the way. But I don't know how big those angles are, but I do know they've got to be equal to each other because we showed that x, y, and y, x, z had to be equal. Make sense? So you see the marriage of geometry and algebra. Isn't it fun? All right, number 7. Here's another fun one. Read this for us if you would. I think we're to Quentin again.
Find x, y, and or for L.
Number 7. We're going to skip number 6.
Okay. Find length of the altitude on the non-equal side of isosceles triangle ABC. We call that this altitude of an isosceles triangle bisects the base.
All right. Read that again for us, Jamie. I feel like this is like those proofs in geometry where you're like reading it and you're like, I don't even know what I just read. Read it for us again.
Find the length of the altitude on the non-equal side of the isosceles triangle ABC. Recall that this altitude of an isosceles triangle bisects the base.
All right, so if this were a proof, right, I'd start by saying, so what picture do I draw? What's the main shape? But it's specifically going to be an isosceles triangle. The problem is, I don't know which sides are equal, right? It doesn't tell me. So I'm going to draw a triangle, and once again, I'm just going to draw a triangle that's almost kind of equilateral-ish, because I don't know which of the sides are equal, but I've got this triangle ABC, and I know it's going to be isosceles, which means there's going to be 2 equal sides. But it wants me to find the length of the, well, the altitude that goes to the non-equal side. Now, hold on now. Altitude. What does altitude mean?
From the top to the base.
From one point perpendicular across. So remember, technically there's 3 altitudes, right? I could draw an altitude here, I could draw an altitude here, I could draw an altitude here. And by the way, remember the altitudes would all intersect at the orthocenter. That's a free term that's going to come up in another lesson or 2. One of these altitudes is the one I'm solving for. It's the one that goes to the non-equal side. But I don't know which one's not equal yet. So guess what we need to do? Find all 3 lengths. I'll erase the one that the 2 that we don't care about. So go ahead and find all 3 lengths just so we can figure out which one's the non-equal side. Find the length of AC, the length of AB, and the length of BC. Given All right, so hopefully you got AB's length to be square root of 58 units, BC's length to be square root of 58 units, and AC's length to be originally square root of 116. We can reduce that down to get 2 square root of 29 units. All right, so that means the legs of the isosceles triangle are which two sides? BC and AB. Those are the legs. Normally then, I would have those two sides upright, and my base would be the non-equal side. Okay, so normally AC is the side that I would rest this triangle upon. And so it says, find the length of the altitude. Find this length right here. Well, in order to find length, I need to have 2 points, right? I know point B. What is this point here? Well, it reminds me in the second half of the question, Quentin, that
the altitude of the isosceles triangle bisects base.
Yeah, you remember this picture, hopefully from last year, and we said if you draw this line, if you know that it's perpendicular, altitude, bisects the base, bisects the vertex angle. If you knew it bisected the vertex angle, you know it's perpendicular to the base and bisects the base. If you know that it bisects the base, it's perpendicular to the base, bisects the vertex angle. Remember that line? Special line? Well, here, they're telling us that this is the altitude. Well, we know there's at least one altitude you can, or only one altitude you can draw. They're telling us, okay, this altitude, that this line that's going to be perpendicular, find its length. But if it's perpendicular, then it bisects, which makes the foot of the perpendicular the midpoint. So now, let's find the midpoint of AC. Now let's find the midpoint of AC. And what do we get? 11, 8. Remember, you're going to add 22, divide by 2, 11. Add 16, divide by 2, 8. Or think what's halfway between 9 and 13 is 11, what's halfway between 3 and 13 is 8. However you want to think of it. So what we're finding, to find this length, here's the notation here. We're going to find the length or the distance from B to the midpoint of AC. So subnotation with subnotation. It's great. Makes you look really smart if you do this on your homework paper and then show it to your parents. So what is the length of the altitude at your seats? Interesting. And what do we get? Square root of 29 units. Now, something that's really interesting. If you were to take the square root of 58 and the square root of 58, either of them, right? And we were to multiply that by the square root of 2, what would it give you?
Square root of 116.
X times the square root of 2. This isn't just an isosceles triangle. What is it?
45.
It's a 45, 45, 90. This is apparently a 90-degree angle. Obviously not drawing a scale, right? And apparently these are 45-degree angles. It's a kind of interesting observation there. Right? All kinds of geometry things we can take from the algebra that we do. And by the way, interesting as well, if you were to find this length, it'd be the square root of 29. If we find this length, it'd be the square root of 29. We already said that this length is the square root of 29. Remember that this point, the midpoint of the hypotenuse of a right triangle, is equidistant from all three vertices. It is the circumcenter, the midpoint of the hypotenuse of any right triangle, in this case the 45, 45, 90. All kinds of cool geometry stuff that we can take from this. Quentin, don't look so distressed. All right, anyway.
I know something else is coming.
Well, we'll stop there for now. I'm going to give you 3 problems similar to these that you're going to do for homework tonight. Page 204, I want you to do 4B, 5B, and 7B. Page 204, numbers 4B, 5B, and 7B. And we'll take a look at those in our next lesson. But yeah, all kinds of geometry terms and geometry facts going to start coming back to us here. And some great observations that we can make from the numbers we get from our algebra. All right, well, have a wonderful rest of your day. And when the bell rings, you'll be dismissed.